All right, Mathletes 3.2 polynomial functions. So a polynomial function takes this form where we have no x's in the denominator. We have no x's under a square root or to fractional powers. All our x's are to powers, and we put our highest power first, and typically they're going to have coefficients in front of our x, and we end with a constant term, or you can think of this as x to the 0 power, which is 1 there. And all those have to be real numbers, no imaginary numbers there. N needs to be non-negative because we know if our power is negative, then that's actually a fractional, and that's not going to be a polynomial, so we don't want those. So n, your largest one, is the degree of that polynomial. Okay, and the domain of polynomials are always a set of all real numbers. You can always plug things in and get values out. So here we want to look at some functions, and we want to decide if it's a polynomial, what degree that polynomial is, the type of polynomial it could be, and what its end behavior is. End behavior is going to be what happens on the extremes as we go to positive infinity and negative infinity on our x-axis. What's happening to our graphs? Is it ending high or is it ending low? So f of x equals 3. Is that a polynomial? Well, we're going to say that's a yes, it is a polynomial. We're going to call that a degree 0 because it is constant. When you look at our graph, we can see it's just a horizontal line, so our end behavior is horizontal. Okay, so our second function here is 2x plus 7. Well, that's a line, and yes, that is still going to be a polynomial. Okay, our degree is 1 because the x has a coefficient of 1. We call this a linear function, a linear polynomial. And notice this end behavior. We have one end ending high, and we're starting low. So down on our graph, you can see here, we're ending low, starting high. Okay, so for the next one, we have x cubed minus 7. So notice this is going to be a polynomial. Okay, we call this a third degree polynomial, and this is a cubic. Okay, and notice our end behavior. Again, it's ending high, starting low from the left. So we are like that. So end behavior, we'll just put arrows letting us know if it ends in the negative or ends positively. Okay, well, f of x equals x times x minus 2, we can see is going to be a parabola, because if we distribute that x through, it's going to be x squared, so that makes it a second degree polynomial. Okay, and again, this is called a quadratic. And this quadratic, notice this one, we are going to start high and end high as well. Okay, 4x squared minus 3x plus 3. So if we look at that function again, it's just going to be a parabola. So yes, again, it's a degree 2. It's a quadratic, and it starts at high, ends high. Okay, well, f of x equals the square root of x. Well, if we remember, the square root of x is x to the 1/2 power. We cannot have fractional exponents, so this is no. And again, another way you can tell it's not a polynomial is because we don't have a domain over here. We have no values over here in polynomials. The domain is always all real numbers. So the next one, x squared minus 5 over x squared. This is a rational one. If we graph it, okay, you can see we're going to have an issue right here at -1, where we're not going to have any values, and we're going to have a hole in our graph. So that's not a polynomial. Okay. The last one is square root of 3 x cubed plus 5. And this is a polynomial. Don't be thrown off by the square root of 3 here. That's just our coefficient, and we can have coefficients as long as they're real numbers. Square root of 3 is a real number. Okay, so this is a degree 3 because of that. And we know that this is a cubic, and this cubic is starting low, ending high. So graphs of polynomial functions, we need to understand that they're smooth and they're continuous. There's no gaps, holes, or sharp corners. We have no points or corners on our graphs. If we zoom into an area like this, even though it might look pointed, it is going to be rounded off there, and it's not ever a true point. Okay, so we're going to be talking about end behaviors and turning points. So end behaviors, like we said before, is what is happening at the as we go far left and far right to infinity, what's going to happen to our graph. Turning points is where we go from positive slopes to negative slopes. So we have a turning point here, a turning point here, a turning point there, and a turning point there. So with 4 turning points, okay, the number of turning points is at most the degree minus 1. So if you think of a parabola, that comes from a x squared graph. You have 1 turning point. So it's always 1 less than your power. So here, this looks like maybe a power 5. So a x to the 5th type graph, power graph, because we have 4 turning points. That's 1 less than 5 there. Okay. The ends of the graph, the extreme left and right, resemble the power function of the same degree. Power function is just ignoring every n minus 1, n minus 2. You're only looking at your highest degree polynomial. So with the highest degree, there's some things to remember. If it is even, so that's something like x squared, x to the 4th, x to the 6th, and so forth. If those are the power functions, they are going to end high, start high, end high. Or if your coefficient in front of it, so if you have negative x squared, negative 5x to the 4th, doesn't matter what that coefficient is, but if it's negative, then it's going to start low, end low. I always like to just think of this like a parabola. I know that parabolas that have a coefficient in front of it that's positive are going to start high, end high. And when that a coefficient's negative, it's going to end low and finish low. And that's going to be consistent through all even degree polynomials. So we'll also have odd degree polynomials, okay, like x or x cubed or x to the 5th. When those are, you know that they're going to start low. If you think just basic linear function, okay, that's an odd polynomial. It's going to start low, end high. Or if that coefficient is negative, so we could have negative 2x, negative 6x cubed, negative 1/2 x to the 5th, and so forth. If there's a negative coefficient, it's like a negative slope, so you are going to start high and end low. All right? So zeros of polynomial function. F of r is equal to 0, then r is called a real 0 of f, or root of f. If r is a real 0 of f, then we can assume these 3 things. R is an x-intercept, x minus r is a factor of f, and the number of zeros is equal to the degree. Multiplicity. When the same factor x minus r occurs more than once, for example, x minus r to the m has a multiplicity of m. So if that multiplicity is even, then the graph touches the y-axis. So on some graph, if it's even, instead of going through, this goes through your axis, you might have a graph that comes down, just touches it, and then comes back. This would be a even multiplicity. Okay. If m is odd, then the graph crosses the x-axis. So we can see that these are odd multiplicities in this original graph because it doesn't just touch, but it goes through. So notice that if it's just x minus r to the first, we can still consider that an odd multiplicity because it's a multiplicity of 1. So if we're given a problem and we are asked these following questions, if I want to find the degree, I want to take the sum of all of these. So I know that this is x squared, this is x to the first, third, and second. So if I add all of those up for all the factors, that's 1 plus 2 plus 3 plus 2, that's going to be equal to 8. That is my degree of my polynomial. I can think of it, well, if I multiplied these all through, that'd be, well, first of all, this is squared, so I'd want to square that first, so that's a quadratic. If I multiplied it by x, it'd be x cubed. Then this is a cubic, and x cubed times an x cubed is x to the 6th, and then x to the 6th times something x squared. It's going to be x to the 8th, and a bunch of different things at the end. Okay, but all I'm concerned about is the degree, so I can add up those powers there, and I can see that that's a degree 8 polynomial. So x-intercepts. X-intercepts, I can see from the first one here. So this one here, okay, that first term, I'm going to get an x-intercept at 0. Is going to be 0. Another x-intercept is coming from this one. Okay, and that is going to be when x is 3. It's going to cross the x-axis. From this one, the third one, I'm going to have a x-intercept of 1. So it's going to make that 0. And I can see from this fourth one that it's going to be negative 4 is 0. So I know that the graph is going to cross or at least touch at all those places, and those are going to be my x-intercept. Well, to find my y-intercept, I just let x be equal to 0. So I do f of 0 equals 0 times negative 3 squared. And the thing here is I can continue on, but because I have this 0, it's going to be equal to 0. So I'm going to have negative 1 cubed, and I'm going to have 4 squared. Well, that's equal to 0. So I know my y-intercept is going to be 0. My end behavior. So my end behavior, I have an even degree polynomial. So I'm either here, it's going to start high, end high, or start low, end low. And so what distinguishes this is my a value. So if I look at all my x's here, I notice that they're all positive, so that this x to the 8th is going to have a positive 1 there, a term. There's no coefficients that are negative. So because it's positive, it's going to be kind of like a parabola with a bunch of turning points in the middle, but I'm going to start high and end high. So at each of the x-intercepts, so that's one reason I numbered these. Okay, so this x-intercept 1 here at x, okay, or let's call this at 0. What's happening there? Well, the multiplicity is 1, so what's happening? It's going to go through, or let's just say it crosses there at 0, 0. At 3, 0, okay, that had a multiplicity of 2. So because that's an even, it's just going to touch the axis. Okay, and then here at 1, 0 as a multiplicity of 3, so it's going to cross because 3 is odd. And then at x plus 4, that gives me a negative 4, 0. At that place, because the multiplicity is 2, again, that is just going to touch. Okay, let's look at another example here. So if we're asked to form a polynomial function whose zeros and degrees are given, so we have a 0 at negative 3, and 2, and it's a degree 2. So that polynomial could be f of x equals x plus 3 and x minus 2. I know that's going to be a degree 2 polynomial, and it's going to give a 0 at -3 here and a positive 2 here. I could put anything I wanted here, and it's still going to hold true. I could put 59, and that a value isn't going to change my zeros or the degree of that polynomial, so we could get a range of answers there, a whole family of functions with those two being zeros. Okay, if I have a 0 of -2 and a multiplicity of 2, so I'm going to work this. So x plus 2 gives me that 0, multiplicity of 2, so I'm going to square it. 5 multiplicity of 3, so that's x minus 5, will give that 0, multiplicity of 3. And a degree 5, well, I can see that 3 plus 2 is 5, so this is my polynomial with those characteristics. Should also be able to build a rough sketch. And again, just on B, we could have multiplied this by any scalar we wanted. We could have put -3 there, and we'd still have those characteristics met. Okay, so here from the graph, a couple of things I want to pick out. I want to pick out my zeros. So here at x being -1, I get a 0. So that's going to give rise to a factor of x plus 1. But notice right here it just touches, so it must be an even multiplicity. So let's just do 2. We could do 4 or something greater if we wanted to. Here there's a 0 at 0, so that is going to be represented by there. It goes through, so it just has to be odd. I'm just going to leave it as x. It is to the power of 1. And then for this one, I need to make sure that I have a 0 at, let's see, that's 1, 2, and 3. So that's going to give rise to a factor x minus 3. And because it does go through there, it needs to be odd. I'm going to just make it 3 here. Okay, if I look at this polynomial, I got to make sure my end behaviors work. So ends high, or starts high, ends high. So it's got to be even. And I notice when I do a 2 plus a 1 plus a 3, that's a 6-degree polynomial. Even, all my x's have positive coefficients, so it should match that graph close enough to that. All right. So here we're putting it all together. So first thing we have to do is identify our degree. So I have a degree 1, degree 2, and a degree 1. 1 plus 2 plus 1. This is a degree 4 polynomial. Notice I have a coefficient, an x with a negative. So eventually when I multiply this out, my power function is -x to the 4th power. And that end behavior is going to start low, end low. It's like a concave down parabola. My y-intercepts. So my y-intercepts is if I let x be equal to 0. Well, I'm going to get -0 times -2 squared times 1. Well, that's going to be equal to 0. So my y-intercept is 0. My x-intercept, well, from this one, I get an x-intercept of 0, 0. I'm going to get another x-intercept at 2. And then here I get an x-intercept of -1 there. Okay, my domain is going to be for all reals, x's. And then my range, I'm going to try and graph it first, and I want to get some ideas around what's happening here. So when I sketch this, I'm going to graph some of my zeros. So I have a 0 at 0, 0. I have 1 at 2, 0. And at -1, 0, I have another one. Okay? So I need to figure out my minimum value, or my maximum value, because if I have a graph that's going down forever, I know that for my range, it's going to be for all real y's, such that I'm not going to have an issue with going to -infinity because they're going down forever. But that means at some point there's got to be a maximum in there. So I need to be able to find my maximum. So I'm going to use my graphing calculator. So I go ahead and put the function into my y equals, and I do a zoom 6 to get in the standard window, and I get this graph. Okay, it should make sense here at 1. From here, it's a multiplicity of 1, so it goes through. And then at 0, it's a multiplicity of 1, so it goes through. Here at 2, it's a multiplicity of 2, so it's just going to touch. So as I sketch my graph here, I know I'm going to go, it has to start low, go through here. It's got to turn around, go through here. And I got to end low, I know that. And I know I need to touch just at 2. So I'm going to come up, touch, and come back down. And that's how I can process that. So I need to know this because that's going to define my range. So to find my maximum, I'm going to do second calc and find my maximum 4. And I'm just going to type in, I know left bound, I can go to -3. And my right bound being 0. And then I can make a guess. And I'm going to get a value of 1.62. So 1.62 is my maximum value there. So as I define my range, it's going to go from -infinity to 1.62. Okay, increasing and decreasing. Well, that's going to be on intervals. So on the interval, so from below, from -infinity to this maximum, okay, and we know that that maximum is at -0.6. So here there's -0.6. We are going to be increasing. Okay, so then at that point, at -0.6, we're going to start decreasing. I need to find that minimum point. Well, then I'm going to bring out my calculator. Second calc. Find my minimum there. Left bound, I'm already there. I'm going to hit enter. Right bound, I'm going to push 2. And I guess just scroll over somewhere in between. And I get a 0.84. So I'm going to be decreasing from -0.6 to 0.84. Okay, is decreasing. And then I'm going to be increasing on that interval to from 0.84 to 2. And then from then on, it's going to be decreasing to infinity. All right, that concludes our notes for tonight. Please highlight any questions you have. Bring them to class tomorrow.